Swayam Prabha, free DTH channel for education.
Okay, now what we are going to deal, okay, we have defined the derivative. Already we have derived the heat equation or wave equation and other equations which we have seen, partial differential equation. In the modeling we have did something. Now what we are going to do is that we are going to define the we are going to define a partial derivative. Okay, partial derivative means, see here I have a x here, I have a x here. Okay, x curve is here, x line is here, and f of x is here. Okay, x is here and f of x is here. I have defined a curve like this. Now, once we come for the partial derivative, at least two variables will be involved. So in that case, I have instead of x and y, okay, I will have third direction will come. So z is also going to come. Okay, means I have z equal to f of x. Okay, that is going to be f of x y means it's going to be a real valued function. So that is going to be something like, in the case of f in the derivative one, we can't define x to r. Now here we are going to define from x cross y to r. I have to define, okay, and then I have to define. So this I define like what is f of x comma y equal to something I have to define. Okay, for example, I can say sin x plus cos y. I can define, or I can say x plus y. Another function I can define. So these are some of the second real valued functions in two-dimensional variable. So in the two-dimensional variable, once we have this one, the question is, can we find the limit of this the same way? For example, I can say like what is the limit of x1 comma, suppose I fix y. Okay, I fix the y. Let's say like a, let me fix it as b. Then I'm going to take two things. Okay, so I have to take x1 tends to a, yn tends to b. Okay, or I can say like x1 comma yn tends to a comma b. Okay, so in this case, what I'm going to say is that I'm going to check what is going to be f of x1 comma yn going to, that I'm going to check. See this x1 comma, when I say x1 comma, when I say x1 tends to a, okay, in the real line, it is meaning that in the real line, either suppose this is a, either it can approach from this side or it can approach from this side. Whereas once you come for x1 comma yn tends to a comma b, okay, so in that case my point is somewhere here, a comma b somewhere here. Okay, I can approach in any direction. I can approach from here to a comma b, I can approach from here to a comma b, or I can just keep my b pixel and approach from xn, and I can keep my a pixel and I can approach from here. Something similar to that, I can just get many different curves are there. Okay, for all these combinations you got to check whether it is going to come or not. Once you are checking for the continuity, etc. Okay, now suppose you take any sequences. Okay, any sequences if you take, you got to check whether your f of xn comma yn is going to be approaching f of a comma b, that you got to check. Okay, suppose if you are checking that, so I'm just straightly going to that advanced thing like continuous, etc. So that one we got to check. Then you can define the same logic whatever you defined in the continuous limits, etc. Okay, so that part I'm just leaving it right now. We just explore it. How do they define? Now we are going to define how do we get the limit of the partial derivative. Okay, partial derivative we need to define. So for that, what I'm going to do, suppose a comma b is given. Suppose b is some domain, subset of r cross r. Okay, subset of r cross cross. I take a point a comma b in D. Now what I'm going to find, I'm going to find the curve of, I'm going to find what is the derivative, partial derivative with respect to one of the variable. Okay, so in that case, suppose I want to find a partial derivative. Okay, what I'm going to find is that first a comma b belongs to D is there. Okay, for this I want to find that. For example, I have a curve like this. Okay, I have a curve like this. It's a surface is going to come, because the three-dimensional one is not going to be a curve. It's going to be a surface is going to come. Once it comes to the surface, what I have is I have the point A comma B is there. Now you take, okay, you take a knife or take a big plate which is parallel to which is exactly y equal, which is parallel to y axis. Okay, means you take a plate and cut it over here. Okay, once you are cutting it over here, what is it going to come? This is going to come like this is going to give me some. So since the surface, okay, so we are going to get one curve is going to come. Okay, so therefore one curve is going to come. For that curve, where is it going to be? Means you are going to take that curve. That curve is going to be in the plane xy plane. Okay, so for example, if I take that means I can just project it in the xy plane like this. 2-dimensional is going to come. From the 3-dimensional, I'm going to move to the 2-dimensional. Okay, so you have a curve, you have a surface, cut it using a plane. Okay, that cut is going to give you a curve. That curve is going to be in a 2-dimensional plane. Okay, in that 2-dimensional plane, once we move over there we can define what is the derivative. Okay, what is the derivative I can define. So that is going to give me the idea of partial derivative which you will see. Okay, so let us see what is that with respect to x we are going to see. Okay, so for example, that's what I have defined. So the gray color one is called the surface. For that surface, I am taking a big knife, okay, a big plate, which is cutting the surface. Once it cuts the surface, you are going to get the blue color line. The blue color line is going to give you the curve. That curve is going to be a 2-dimensional. Okay, means it is going to be a curve. So for that curve, what I am going to do is that I am going to find the slope of that curve. Okay, the slope of the curve. Then once again, I got to approach the same thing. When x tends to a, what is the tangent or corresponding tangent I got to find. So the derivative, because it moved already, we already moved from 3-dimensional to 2-dimensional. In 2-dimensional, I know how to define the derivative, which I have defined. So in that derivative I defined, so that I call it as a partial derivative. Let's see how do we define that mathematically also. Okay, this is the basic. And define is that we are going to define the partial derivative of f of x with respect to x at the point a comma b we are going to define. Okay, so a comma b is given here. Now what we are going to find? We are going to find the partial derivative of f with respect to the variable x you have to. Similarly, you have to define what is the partial derivative with respect to the variable y also you have to define. So as I mentioned already, once I am defining the partial derivative with respect to x, what you have to do is that you have to keep your b as constant. Okay, your b is going to be constant, means you are going to cut it using, you are going to cut that using the plane y equal to b. Okay, and then we are going to find that. So in that case, I am going to define this way: fx at a comma b. Okay, f of x at a comma b is same as dou f by dou x. I define that. Okay, a comma b. Okay, equal to, I am going to define df by dx. Okay, so here I go to define, okay, I'm going to define df by, I'm going to keep b as constant, so I'm going to define x comma b, okay, at x equal to a, equal to a 1. What is the definition? Now what is this one? We know I'm keeping b as constant, therefore I got to apply limit h tends to 0, okay. I got to find the neighborhood nearby a, okay, therefore I got to find some neighborhood a plus h, okay. Let's say like a minus h to a plus h you got to find, okay. It's a minus h to a plus h you got to find, and then you got to do the same kind of logic whatever we did earlier. So in this case, what we are going to get? We are going to get f of x plus, so x is going to be a, so I'm going to replace this a plus h, okay, comma b, because second variable is fixed, minus f of a comma b divided by h. So this is called the definition for partial derivative with respect to x. Can you define a similar thing for fy? Yes, of course. So that is going to be as follows. So for fy, what we are going to do, same thing, fy at a comma b is going to be dou f by dou y at a comma b, okay, equal to df by db dy of here x comma b. So here it is going to be a comma y. Okay, here x comma b is there, here a comma y is there. Equal y equal to b is going to be. Okay, here x equal to a, here y equal to b. Same way you can define limit. I'm going to define new variable here. Okay, k tends to 0. Okay, f of same thing. Here a is fixed. Okay, you got to vary only with respect to y. So I am going to call it as b plus k. Okay, b plus k minus f of a comma b divided by k. So this is the definition for partial derivative with respect to the second variable. Okay, so So provided these two limit exist, then we say that the partial derivative is just to x and y will be different. So for example, there are some problems here. Okay, so ux plus uy is there. Okay, so you'll see that some of the examples also. Suppose I have problems like, okay, I got to find what is my ux and uy, etc. Okay, and you can see like what are the values for them. Okay, so for example, u equal to e power x minus y is there. Now what is ux is going to be there. I got to keep y as constant and then I got to differentiate that. Therefore, this is going to be e power x minus y into, okay, e power whatever is there as it is into, I got to differentiate with respect to x, that is 1. Okay, therefore, this is going to be e power x minus y. If I want to find uy, that is going to be e power x minus y, and then I got to differentiate the x minus y. So with respect to x, it is going to be 0. With respect to x is going to become 0 because we are differentiating with respect to y. So into y, if you are differentiating, it is going to be minus 1. Therefore, you are going to get minus e power x minus y is going to come. So if I find ux plus y, uy, this is going to become 0 because this is e power x minus y, this is minus e power minus xy, it is going to become 0. If I put ux minus uy, then it is going to become like e power x minus y, minus of minus or plus is going to come. So 2 times e power x minus y is going to come. But what is e power x minus y? That is u. So I can write as 2u. Same way, now you can define from here uxx also you can define. Okay, uxx is you are defining, you are taking the derivative with respect to x again here, whatever is here. So e power x minus y into 1 is going to come. Therefore, it is e power x minus y. Similarly, I can define uxy. I can define. Okay, uxy is going to become. I have to differentiate this with respect to y. Therefore, e power x minus y into minus 1 is going to be there. Therefore, this is going to become like minus e power x minus y is going to come. Okay. Same way, from here, okay, from here I can define uyy. So uyy is going to become like e power minus e power x minus y. Okay. Into again I have to differentiate with respect to 1. With respect to y, so minus y, another minus is going to come. Therefore, it is going to become like e power x minus y is going to come. If I define uyx, you can see that this is going to become like I got to differentiate with respect to x. I got to differentiate. Okay, minus e power x minus y with respect to x. Therefore, 1 is going to come. Therefore, this is it. So you can observe that. Okay, you can observe that uyy. Okay, this is uxy. This one and this one is same. Okay, uxy equal to uxy equal to uyx. You can see that. This is not going to be true in general. Okay, if it is continuous and other things are there, then it will be correct. Now, once again, you need to calculate what is uxx plus uyy. Okay, if you calculate uxx plus uxx plus uyy, again this is going to become like uxx plus uyy. Okay, submitted these two terms submitted, that is going to become like 2 times ex minus y, that is u. So 2u I can put it. Now uxx minus uyy, that is 0. Okay, so this also true. This is the so this one is almost, this is similar to what we have in the wave equation, where we have utt is equal to c square ux is there. So something similar to that. So you can expect that some of the solution is going to be at least. Okay, so these are the things. Then we have question again. Okay, so in the first once we deal with the derivatives, okay, we have seen some examples. The examples are like f of x equal to 4x square. Okay, then we have defined what is f dash of x. F dash x was 8x. Okay, now suppose f of x is going to be x square, 4x square. Then what is f dash of x? F dash of x is nothing but 8x. Now question is, suppose this is that, then the question is that suppose f dash of x is given. So f of x is equal to 4x square means f dash of x is equal to 8x. Now suppose f dash of x is given as 8x. Then can you guarantee that f of x is always going to be 4x square? Okay, can we guarantee this one? We cannot guarantee that. For example, suppose if I take, okay, my f dash of x is going to be, let's say 4x square plus 5. Okay, then also I will get that f dash of x is going to be 8x. Okay, similarly I can put f of x equal to some 4x square plus some 7. Okay. In that case also I can find what is my f dash of x. F dash of x is going to be 8x. In general, if you put f of x equal to 4x square plus some c, some constant, then also f dash of x is going to be 8x. So these are all the possibilities are available. So that means if I give f of x, your f dash of x, whatever you find is going to be unique. Okay. But if I give a f dash of x, okay, if I give a f dash of x equal to 8x, then f of x is not necessary that it is going to be 4x square. It can be 4x square plus some constant. Some constant is going to come. Okay. So that means it is not going to be unique. If I give a curve, its tangent is same. Okay, its tangent which you are finding, or the f dash of x you are finding, that is going to be unique. But if I give the tangent, okay, for that it is not going to be same because family of curves are going to come. For example, you can take that. If I take if I give a take is that I'm going to take some constant curve. Okay, I'm taking a constant curve here. Okay, then what is f dash of x is going to come here. So it's constant curve. So let's take like f of x equal to 1. Okay, it's a constant curve. So in that case, what you are going to get is that you are going to get the derivative is going to become 0. Dash of x is going to become 0. Instead, if I take f of x equal to 5, okay, let's take f of x equal to 2 or f of x equal to 5. Okay. So in this case also, what is my f dash of x? That is going to be 0. Means if you take any 0 derivative, okay, the derivative is becoming 0. It is not necessary that you are going to get 1 or 2 or 3 or 4. You are going to get infinite number of constant lines are going to come. That means you are not going to get the unique thing. Okay, so that is the thing it is going. I'm going to convey here. Similarly, if you take y equal to e power 5x, then we have found that dy by dx is going to be 5 into e power 5x. Okay, but if I give the dy by dx equal to 5 e power 5x, can we guarantee that y equal to e power 5x? It is not. Okay, you are going to get something different. Same thing for the third one also. Sin x plus x square is going to give you cos x plus 2x. But if I give the dy by dx equal to sin x plus cos x plus 2x, you cannot guarantee that y is going to be sin x plus x square. Some other constant is going to come. Some constant is going to come. In the case of ODE problem. So we have f of x equal to 4x square. F dash of x equal to 8x means we are going to get some constant 4x square plus c1. Similarly, second one we are going to get some c2. Third one we are going to get some c3 is going to come. Okay, so that means the derivative measures the slope of the tangent lines of the given curve. Okay, however, if you give a curve, for that the derivative is going to give you the slope of tangent lines of the curve. But if I give a slope of a tangent curve, okay, suppose you know the tangent line for a you have given only some tangent line. Okay, for example, I can say that I can take some curve. Okay, let's take some curve. For example, this curve I take. Okay, I'm giving a tangent curve. For each one, I'm going to give a tangent curve. So in this case, for example, let's take 4x square, which is nothing but a parabola I'm going to have. So I have some curve here. Okay, suppose I have some curve, either this way or this way. Okay, and you found the tangent to that curve. Okay, you found the tangent to that curve. So that is given in some formula like 8x is there. So it is going to be there. Now suppose tangents are given. Can you find a unique parabola 4x square? No, right? You can find different curves. Family of parabolas you can find 4x square plus. Okay, that is nothing but the family of curves is going. And in some cases, even you may not get a curve also. Some tangent lines are given for which you may not find the curve. It is not necessary that you got to find the curve. It may not exist also. Okay, so it may you may end up with a family of curve, or you may end up with no curve also sometimes. Okay, so that is that. Okay, same thing here. Okay, same thing for the PDE case also. Suppose u equal to e power x minus y is given, then we can prove that ux plus uy equal to 0. Now, on the other hand, I have asked this question. Suppose ux plus uy is given to you, ux plus uy equal to 0 is given. Then can you guarantee that which implies u is equal to e power x minus y? Is it guaranteed? It's not necessary. Okay, that's not necessary. Once again, you will get a similar kind of answer is going to come. Okay, for example, if I want u equal to e power x minus y is that you don't need to, you may not get that u equal to e power x minus y. Okay, in general, if I take something like instead of u equal to e power x minus y, suppose u equal to some f of x minus y is given. Okay, in that case also you can find a ux plus uy equal to 0. For example, what is ux here? Ux is nothing but f dash of x minus y into 1 is going to come, so that is going to be there. Uy is going to be f dash of x minus y into, with respect to y, I got differential, that is going to be minus 1. Therefore, from these two, we can say that ux plus uy is going to become like f of x minus y minus f of x minus f dash of x minus y minus f dash of x minus y, that is going to become 0. Okay, so in general, it is not going to be unique answer. You can get any functions of this kind is going to satisfy this relation, ux plus uy equal to. Same way, for u equal to uxx plus uyy equal to 2u is given, that can be guaranteed that u equal to e power x minus y. Same way you cannot guarantee that. Okay. So the first one, f of x minus y. Okay, so f of x minus y is, if you take u equal to f of x minus y, you are going to get again same thing. Okay, u dash is going to come like this. So you cannot get a unique answer. Okay, so this one you can find it using method of characteristic, which you will see in the, once we have once you finish the ODE portion. Okay, we'll see that. Also, you can the second equation, uxx plus uyy equal to 2 is given, which is called Helmholtz equation with k square less than 0. So in that case, okay, you can use the separation of variable, okay, to find some solution, or you may need some more assumption to solve this problem. So for getting the uniqueness, what we need extra here is that, for example, in this problem, suppose I give extra condition, I need to eliminate this constant. Suppose I have given some extra condition. Okay, suppose f of x equal to 4x square is there. I give some more condition. Okay, f of 0 equal to, let's say, 2 is there. Okay, then now what I can do is that f dash of x equal to 8x means f of x equal to 4x square plus c is there. I can substitute f of 0 here. So if I substitute f of 0 here, that is going to be 2. On the right hand side, it is going to be 4x square plus c. Since x equal to 0, this is going to become like c. So in that case, I can find that my f of x is going to be 4x square plus 2. Means in that case, I can find my unique answer. I can find. Okay. In general, if it is given only this one, you cannot find. But if you give some extra condition, okay, some conditions if you are giving, then in that cases you can find what is the you can find some unique answers. Or sometimes you will not find the unique answer also. For example, f dash of